Hi everyone, welcome to Unit 1, Lesson 2, where we're going to continue to explore topics with and related to limits. And we're going to round out that first unit in the AP curriculum. So we're going to talk specifically about squeeze theorem, intermediate value theorem, and just a little bit of discontinuity theory, and just a few other tangentially related stuff. So squeeze theorem. Squeeze theorem is a pretty niche topic. It'll come up usually once, maybe on AP exams, but essentially what the squeeze theorem is that if f of x is less than g of x is less than h of x, when x is near a, except possibly at a, then this right here is true. And it's much easier to conceptualize this as just saying as you've got one function, in this case our g of x, is going to be squeezed between two other functions, f of x and h of x here. Because at some point, if this is f of x, and this right here is h of x, and now technically they're supposed to be much closer than this, but f of x and h of x are really close at some juncture, and then our g of x, our third function, the function we care about, gets squeezed in between these points. Then if it's being squeezed in between those points, those functions there at some specific point, then we can look to see what's happening at f of x and h of x to evaluate g of x. It's a pretty niche topic, like I said. It comes up later on in some facets, but like that's essentially all you need to know right now is that sometimes a function can be squeezed between two other functions, and we can use that information to help us figure out what the limit is. Now, of course, when we've got the graph in front of us, it's pretty straightforward to understand. Here's a much better drawing right here where we've got two functions, and then the function we care about is being squeezed in between those two functions. It's officially known as the squeeze theorem, but there's a few other ways that it can be described. Again, with the graph, it's pretty straightforward. Sometimes with algebraically, it takes a little bit of a leap there. So some classic examples when you have to use the squeeze theorem algebraically are when we use sinusoidal functions, because a sinusoidal function like this, its amplitude is dictated by this function right here, by whatever your coefficient is. So we can use this fact to figure out, hey, what's going on as we tend towards zero here? So the limit of this as x tends towards zero. And so the leap that we have to make is to say, hey, I know that a sine graph, its amplitude is dictated by whatever the coefficient is. In this case, my coefficient's x squared. So really I have to ask myself, hey, what's the limit as x tends towards zero of x squared? Because this right here, this is going to get squeezed by this right here, this whole x squared thing. And so hopefully you can see that, hey, this rate here evaluates to zero, because if you just think about x squared as, you know, you get closer and closer to, that's not well drawn there. Let's try that again. As you get closer and closer to zero from the left and right hand side, your function goes to zero, which means this coefficient here gets closer and closer to zero. And so if this first part is getting closer to zero, then the actual amplitude must be shrinking to zero. So at zero then of the overall function, then our limit would be zero. And just we can kind of reverse that, not reverse it, but we can look at another situation that's similar, where we've got the limit of 1 over x cos of 1 over x as x tends towards infinity. And again, because we're talking about a sinusoidal graph, we can use this idea here that the coefficient is going to restrict the amplitude of the cosine. So we have to ask ourselves, hey, what's happening to our amplitude as we put a larger and a larger number there? So what's the limit then as x tends to infinity of 1 over x? And so hopefully you can see that this right here, 1 over x, this is going to be equal to 0, because as you take 1 and divide it by a larger and larger number, you're going to get a smaller and smaller number, which means then that this whole graph here, its limit then would of course be 0 as well. Yeah. So let's see what else we got going here. So identifying continuity at a point. So a function is only continuous at a specific point if the limit of a function as it approaches c is equal to f of c. So basically, your limits have to be the same on the left-hand, right-hand side, and that actual point needs to be defined. You can kind of see it there in small c, comma, f of c is defined. It's a filled-in point if you want to think about it like that. And as long as this is true, then the function's continuous at that point, and possibly other places. Like the entire, that has to be true at all points for the function to be continuous along some defined interval. And if there's a discontinuity there could be discontinuities in other places as well. There could be multiple discontinuities. You could have entire regions that are undefined, but for a specific point, this is the definition that we would use. And so let's actually look at this algebraically here. So here we've got f of x being defined as a piecewise function, and we're asked to explain why or why not the function is continuous at x equals -3. Why at x equals -3? Well, that's where we've got the switch over from square root 25 minus x squared to x plus 7. So in order for this to be true, like the idea is that the limit as x approaches 3 from the left-hand side of f of x has to equal the limit of f of x as x approaches 3 from the right-hand side has to equal f of 3. Like this is what has, like these all have to be true in order for the function to be continuous there. And we remember back from lesson 1 where it's possible for this to be true, and then have a discontinuity at f of 3. So let's check and see what's happening here. So first off, I can see that f of 3 is defined because, or f of -3, these should all be negatives here, geez Louise. F of -3 is defined because I can see that there's an equal to sign here, so I can plug in -3 and get an answer out. And I know just in passing that radicals are continuous functions and linear functions are most certainly continuous. So I know in general I'm talking about continuous functions. Along their domain, I should say. And the domain of a linear function is always defined. And for the square root, I can figure out where the discontinuity, or like where the function starts. And we'll see if that comes into play as we're solving it. So I'm literally just going to take -3. I'm going to plug it into both. So if I have the square root of 25 minus -3 all squared, is that equal to -3 plus 7? So what I'm doing is I'm taking this -3 and I'm plugging it in here, and I'm taking this -3 and I'm plugging it in here, with the idea of seeing, hey, is it true on both sides of that piecewise function? So this will be the square root of 25 minus 9, and 25 minus 9 is 16, and so the square root of 16, square root of 16 is 4. So -3 plus 7 is going to be 4, and lo and behold, 4. So because it's the same point, like it tends to the same number on both sides, then this function is a continuous function. So what this looks like, if I just drew a rough graph of it here, so x plus 7, so it's a -3, I see a switch over. So square root of 25, so it's, what did I say, it's 3 and 4. So it's going to look something like, you'll have this, and then a linear function like this. And because, they share that point there with it being specifically defined on the radical side of it, that it is continuous at that point. So a function is only continuous along an interval if it's continuous at each point along the interval, something I alluded to earlier. If the above statement is not true, then the function is discontinuous at least one point along the interval. And some quick facts: all the basic functions that we've worked with up till now are continuous on all points in their domains. I know that might seem funny to say it like that, but that is a truism for our pre-calc 12 and before functions that we work with. Okay. Now, I've already talked about some of these just out loud in passing, but here are the formal definitions of our types of discontinuities that we could have. So we have a removable discontinuity, which is literally a hole. And algebraically, these arise for when you have a situation like you have x plus 1, x, what would that be? Let's say it's roughly -2 all over x minus 2. You're able to cross these off, but it still creates it's still undefined at that point. Obviously, this doesn't model this sinusoidal graph here, but just as an example, that's how removal discontinuity arises. A vertical asymptote arises when you can't remove it, like you can't cross it off like that. So in this case, this is like something over, what would that be, x minus 3. And x minus 3 can't be removed from the it's just always there. So at 3, it's an undefined function, and that's what creates a vertical asymptote. And jump discontinuities are when you have non-continuous piecewise functions. So, you've got some function modeling up till 2 pi, and then after 2 pi, there's some other function modeling it. Now, in passing here, I see that I've made a boo-boo in these notes, and I'll try to change it on the ones I share with you. They actually can't both be defined here. Do you see how I've got a filled-in dot here? So that actually means that this isn't a function, because for every x value, in this case it's 2 pi, you can only have one y value. But here clearly it's implied that there's two output values. So when you're having a jump discontinuity like this, one of them should be an empty circle, and the other one should be can be a filled-in circle. It's okay to have both two empty circles. It's not okay to have two filled-in circles. So that's just a minor typo there, and I will fix that for your notes. Removing removable discontinuities. Two negatives make a positive. So if you ever want to fill in, or for whatever reason need to fill in removable discontinuity, the quickest way to do that is to actually make a piecewise function, and then at the point of the discontinuity, redefine what that point is. So like, let's say this is f of x is equal to, and then you'll have the sinusoidal function up top, and then you can just literally say, what is that, 2, 4? You can literally say 4 at x equals, that looks to be approximately 2. And so you can actually define that point at specifically that x value. That's how you can remove a removable discontinuity. IVT. So IVT is important, and one of those things that always gets asked, usually multiple times on the AP exam. And so intermediate value theorem, always abbreviated to IVT, and that's acceptable to use when in your final answers and stuff. So what it's saying is that a continuous function picks up all y values on an interval for which it is defined. So provided that our domain is a B with hard brackets here, where like f of a and f of b are included, between these 2 points, between f of a and between f of b, it's going to pick up all values between f of a and f of b, which might sound funny or might be something like you've never really reflected on. But essentially, like if this is 3 and this is 5 and the function's continuous along that domain, then it's going to pick up 3.1, 3.2, 3.3, 4.79. All those values will be present within that domain, as long as it's a continuous function. So every value between 3 and 5 will be present. Now, values beyond those could be present. As you can see here, clearly it's going above, if this is a 5, for instance, clearly we've got a section of it going above 5. That's just a quirk of this specific example here. However, that's not guaranteed. That's not something that you can say using IVT. The only thing that IVT says is that all values can be or will be picked up on a continuous function between the endpoints, because we can boil a function down to just a straight line between a and b. And on a straight line between a and b, we will, of course, pick up all values. So that's something that will come up and will it'll always be present on an AP exam. It's one of those things that always gets asked. And just a wording note, wording is extremely important in these questions. You always need to reference your endpoints, and you need to reference the fact that it is continuous. So usually you would say something along the lines like, given f of x is continuous along like a and b, and you would actually fill in what these numbers are. Then according to IVT, 4 is, f of 3 is equal to 4 is a true thing, or whatever they're specifically asking about. But you do want to clarify in your first sentence when you're answering these questions to say, like, given f of x is continuous along the domain of AB, whatever AB is, then according to IVT, and you would also reference the fact that you're using IVT, and then say whatever the point they're talking about is present. So let's look at some quick examples here then. So given that f of x is a continuous function along the domain -4 to 28, answer the following questions. So I might be asking, how come they're telling us this right here? Well, they're telling us this because we just have tables of values. So if they didn't mention the fact that this was continuous, then f of x literally just might be a series of points, and we can't, use IVT at all if that was the case. But they tell us it's continuous, and it's continuous along this domain, which just happens to be where our table starts and where our table ends. So that's good. And we're asked to answer the following questions. So is there some value c for which f of c is equal to 7? So I don't see 7 here as an output, but is there some value for C which will give me a 7? So in order to do this, I have to look to see like what my range is, and I'm using that like as we talk about functions. What's the range? So I see I range -5 seems to be my lowest, and my highest is 14. Now, just to be clear, that's not always going to be true, but like we always want to look to see what's happening at the endpoints because that's the only time we can guarantee what's going on. So here I see that basically if I'm looking at -4 to -5 gives me a point here, and then 2814 would give me like a point here. So an output of 7 falls in between, like, this is 7 right here. 7 falls in between -5 or -4 and 28. So yes, there is some f of c value which will give us 7. I don't know what it is, but there exists some value given that it's continuous along this domain. Okay, is there some f of c value that will give -10? So if I look here, I don't see anything lower than -5. So -5 is the lowest. So I actually get in this table. So I actually don't know. So I don't know. Like there's not enough information, not enough info. No, not enough info is the best way to answer that question. We just don't know. There could be for f of x, like if f of x looks, something like this, or like, it's just, we don't know. Like there's, given the information present, there's no way for us to guarantee that there is. Same way with A, for us to say as clearly as we do with A. However, with C will fall in line with A because -1.75 falls in between -5 and 14, the extremes on our continuous function that we're given. So yes, there is some C value which will result in that being true. Given g of x is continuous function along the domains 4, 3, answer the following question. So again, I'm going to look to see what's happening here. So it's continuous, so I want to find my extremes. So I see I've got an extreme down to -85, and my highest number looks to be 7. So my endpoints are, it's only continuous along the domain 4, 3. So that would... I actually suspect this is a typo here. I'm going to change this. This should be 413. There we go, 413. So the only thing we know about our function, and I will change that in your notes, is that it ranges from -10 to -85. So these are our points right here. And so let's look and see what the questions are. So explain why we are unable to determine if there's a value c on the interval 1 to 100 such that g of c is equal to 12. So we don't know, because if we're looking at what our domain is, where it's defined, where it's continuous, it's only between 4 and 13, and along 4 and 13, we only get from -10 to -85. So there could be some value, like if the function, spikes up or whatever, and then goes back down. But all we know, because we're just given points in a table, we don't know that like 12 falls outside the range in the table that we have. So it could exist, but we're not sure. And determine if there's some value such that g of c is equal to 5. Again, we've got that same problem where we're only given that it's continuous from 4 to 13, and the only points we know are -10 and -85. So it's the same thing. There could be, we can't say with certainty that there is. So it's possible, but there's not some c value guaranteed to be there. And I believe, some fun just application questions here. So let h of x be equal to f of x divided by g of x. Answer the following. So is there a value c on the interval -2 to 2 such that h of c is equal to 4, h of c is equal to 0? Okay, and we've got a little point here saying that f of x and g of x are both continuous along the domain -2 to 2. Important for us to know. So what I'm going to do is I'm going to make a little column here and call it h of x, just to so I can see what's happening at these points. So h of x is equal to f of x divided by g of x. So f of x divided by g of x gives me -10 here. This will give me -17. This will be undefined. 12 divided by 4 will give me, -12 divided by 4 will give me -3. And then -5 divided by 20 is just the same as +1/4. So I've now got to figure out and see what's happening. Is there a value for c on the interval -2, 2 such that h of c is equal to 4? So if I look to see where I'm ranging to, I'm basically going between -10 and 1/4. And it's also interesting to note here that this h of x is not defined at 0 now, because it was f of x divided by g of x. So whatever h of x is, there's at least a whole, possibly more, at 0. So that is something for us to keep in the back of our mind. So is there a value for c such that h of c was equal to 4? We can't say. Don't know. Don't know. Because there's nothing here, like our range goes from -17 to +1/4. So because of that, 4, it falls outside that range, and we just don't have enough information. We can't say with certainty that there is. We can say for certainty that there is a 0 value, because we at least go from -3 to 1/4. And by the way, when I'm looking at I know that it's continuous from here to here, and it's continuous from here to here. So I have to be careful, and I have to like keep things separate and use information on this side and information on this side to help me answer these questions, because yeah, like it can be dangerous to jump from one side of a discontinuity to another. So I'm just going to focus on looking here and looking down there to see if I can use that information to say with certainty. And I definitely can for h of c is equal to 0. Is h of x continuous along this interval? No, because at x is equal to 0, g of x is equal to 0, which meant that we had to go 9 divided by 0 is equal to. And by the way, there can be other discontinuities, and this is where yeah, like we it's if we actually think about this question here, like we can't even say with certainty that, now that I'm thinking about this here, that even this is certain, because g of x could have been 0 more than once here, right? So like even this, I really don't like doing now that I'm reflecting on this, because of the fact that we have discontinuities here. So we know that. So is h of x continuous? No, we know that for certain. It's at least discontinuous at x equals 0, possibly other places. And yeah, and same thing with this one. This is a question we can't even say with certainty, because of the fact that g of x could be 0 in more than one location. If we had some sort of information saying that g of x wasn't 0 or didn't exceed some value, then we could potentially answer these questions. But yeah, yeah, we just don't have enough information. It can't be clear. There's no guarantee because of the possible points of discontinuity. And finally, extreme value theorem, EVT. So if f of x is continuous along the interval AB, then f of x has both an absolute max and an absolute min on that interval. So EVT, like IVT, is something that comes up on every AP exam, you'll at least once, possibly multiple times. Wording is again important, and basically it might sound funny, again, something that you might have assumed that was always true or what have you, but basically, in order to have an absolute max and min, you have to have a closed interval that's defined, it's continuous along that closed interval. And because without that, and this is actually a good example, if this was an open interval, let's say it was just A, B like this, and you had an open interval and an open interval here, along this interval here, there's actually no absolute minimum. We can have an absolute max because of that point right there, but there is no absolute minimum, because if, let's say this point is 2 comma 2, well, our absolute minimum then would be, because 2 isn't defined, it would be 2.0 all the way to infinity 1, and we can't express this number like that is an irrational number, like it's a number that can't be expressed like without using some convoluted math techniques. So like there is no absolute minimum guaranteed if the function is not along a closed interval of A to B. There still can be, it's still possible to have absolute maxes and mins. In this case, we had an absolute max, but we're not guaranteed to have an absolute max and min if it's an open interval. And just a little note here, the absolute max and min don't have to occur at f of A and f of B. As in this case right here, we have an absolute max occurring at f of whatever that point is right there. And extreme value theorem. Okay, this is what I just mentioned here. The endpoints need to be included in order for us to have a guaranteed absolute max and min. If the endpoints aren't included, and so in this example right here, even though these are the same graph, in this one the endpoints are included, in this one they are not. There is no max and min here. It is not like in this case, there are no, and the EVT states that it has to be closed and continuous in order for there to be a guaranteed absolute max, absolute min. And by the way, just in terms of the terminology, absolute maximum is just the highest point along that interval, and absolute minimum is the lowest point along that interval. Anyways, I know that was a long video. If you guys have questions, please reach out. If not, I'll see you in the next video.